For number 1 here, our first step is to put it into quadratic form. And of course, part of that is making it equal to 0. So let's do that first. This is our higher power of x over here, the x to the 4th. It's positive, so we're going to leave that where it is. So we're going to make this other side over here equal to 0. So we're going to subtract the 2x squared. And we're going to subtract 8. So that right side's now going to be equal to 0. The left side will be 9x to the 4th plus 5x squared minus 4. This is now in quadratic form, and we're going to make the substitution that u equals x squared. So now this will be 9u squared plus 5u minus 4 equals 0. Is this factorable? Let's try it as 3u and 3u. Does that work out? No, it will not. But if we do 9u and just u, or 1u, if we do negative 4 and plus 1, that will work. You could have used the quadratic formula, you'll get the same result. So now we have 9u minus 4 equals 0, or u plus 1 equals 0. Solving this one by adding 4, 9u equals 4, and dividing by 9, u equals 4 over 9. Or on this side, we subtract 1 to get u equals negative 1. Remember, however, we made that substitution. U is actually equal to x squared. So now we have to put x squared back in where u is. So x squared equals 4 over 9. And x squared equals negative 1. To solve each of those, to solve for x, we have to take the square root. So the square root and the squared cancel out, giving us x is equal to, the square root of 4 is 2, the square root of 9 is 3, and of course there's a positive or a negative answer, so positive or negative 2/3 is 2 solutions actually. Square rooting over here, the square root of x squared, x is equal to the square root of negative 1, well there's a positive or negative, so again this is the positive or negative I are the other. So there are 4 solutions here. 2/3, negative 2/3, I, and negative I. And of course what would have indicated that we should expect 4 solutions is that we started out with x to the power of 4. The highest power indicates the number of possible solutions. There aren't always that many solutions there, but it is possible to have up to that many solutions. Any questions on that first one? Okay, did you guys need another minute to finish the second one, or are you ready to go over it? Ready? Okay, so again, we need to set this equal to 0. We just have to subtract the 12. So 3x minus 1 to the 2/3 minus 10 times 3x minus 1 to the 1/3 plus 9 equals 0. Now we're going to have to make a little bit more of an interesting substitution here. U is going to equal 3x minus 1 to the power of 1/3. But with that substitution, this becomes a relatively simple equation. U squared minus 10u plus 9 equals 0. And that's actually fairly easy to factor. U minus 1 and u minus 9 are the factors. giving us that u equals 1 or u equals 9. Now we have to substitute back in the fact that u is 3x minus 1 to the power of 1/3. So 3x minus 1 to the 1/3 equals 1, or 3x minus 1 to the power of 1/3 equals 9. First thing we have to do is get rid of the power of 1/3. To do that, take it to the power of 3. 1/3 times 3 is 1. So that just gives us 3x minus 1. 1 to the power of 1/3 is still, or to the power of 3 is still 1. We do the same over here. Take everything to the power of 3. So this is, again, just 3x minus 1. 9 to the third power is 729. So now we're going to solve by adding 1 here. 3x equals 2. And dividing by 3 to get x equals 2/3. Over here, we add 1. 3x equals 730. And divide by 3. X equals 243 1/3. Are your two answers. Now again, you should substitute all of these answers back into the equations to make sure they work. I'm not going to do it at this point. I assure you that all those answers do work, but sometimes they won't. Did anybody get both of those correct? How about the first one?
Just the first one.
Okay. On the second one, do you think you would have got it with more time, or are you fairly confused by it? Probably? Okay. I'm going to throw one more at you. This one's a little bit simpler, just a little different style. I'll give you a couple minutes to try that one. Okay, so our first step here, again, is to make it equal 0. So we'll have to subtract 3 from both sides. So we get x minus the square root of 17 minus 4x minus 3 equals 0. What are we going to do from there? Well, is this in quadratic form? Okay, perfect. It is not in quadratic form. So getting it equal to 0 really doesn't help any. So what we have to do is we have to treat it as a radical. We have to isolate that square root, isolate the radical. Now what I'm going to do, actually subtracting the 3 was a valid move. Because this is a minus the square root, I am going to add that square root to move it to the other side. So we have it. So on the left side we have x minus 3. On the right side, the 3 is gone. We just have the square root of 17 minus 4x. Now, as you said, we square both sides. So x minus 3 squared is x squared minus 6x plus 9. And of course, the squared and the square root just cancel out, giving us 17 minus 4x. Now we can get it in quadratic form. So we'll subtract 17 from both sides and add 4x to both sides. So we've got x squared. Negative 6x plus 4x is negative 2x. 9 minus 17 is negative 8. And on the right side, we're equal to 0. Is this factorable? Yes, x minus 4x plus 2, right? And of course, from there, just solving each of those, x minus 4 equals 0 gives us x equals 4. X plus 2 equals 0 gives us x equals negative 2. Do both of those solutions work? So back up here, let's try x equals 4. 4 minus the square root of 17 minus 4 times 4, does that equal 3? Well, this will be 4 minus the square root of 17 minus 16. 17 minus 16 is 1. The square root of 1 is just 1, so 4 minus 1 does equal 3. 4 works. How about negative 2? So negative 2 minus the square root of 17 minus 4 times negative 2. Does that equal 3? Negative 2 minus the square root of 17. Negative 4 times negative 2 is a positive 8. 17 plus 8 is 25. And the square root of 25 is 5. Negative 2 minus 5 is not 3. So that doesn't work. Now you might argue the square root of 25 could also be a negative 5, which would work. But in order to define definitive solutions here, we have to accept only the positive square root when we're evaluating that equation. I know that's difficult because when we're solving an equation, we have to take both the positive and negative answers. But when we're evaluating it, we're only going to take the positive. Any questions there? Okay, so at the end of class yesterday, we hinted at this next step, which is dealing with the quadratic inequalities. And we'll start out dealing with quadratic inequalities in just one variable. And what we looked at was we looked at breaking it down. So we might have something like 2x squared minus 3x, let's see here. Minus 5 equals 0, or let's less than or equal to 0. If we factor this on the right side to evaluate this, we have to start out just like we did with our linear inequalities. We have to start out with the equation where it equals 0. We're going to slow down and go a little bit more step by step with them today. And solving this, I can factor this, 2x and x. This will be 2x minus 5 and plus 1. Solving this one here, this should be a 0 there. 2x minus 5 equals 0 would give us that x equals 5 halves, or 2.5. This one here, x plus 1 equals 0, would give us that x equals negative 1. Those are the boundaries that we're going to deal with. So on the number line, here's 0. Oops, I'm going to move it over the other way a little bit. Here's 0. Here's negative 1. Here is 2.5, or 5 halves. And we know that those are the boundaries. Now we have to test to see where would this be true. So I can either just generally look at it and generally analyze, or I can pick a value. probably easier when you're starting out to pick a value. So I know that over here the value -5 is in this range. So let's use the value -5 over here. If I put -5 into this original equation, is it true? I put -5 in there. -5 squared is 25, so that'd be 50. -3 times -5 is a positive 15, minus 5. Well, that actually ends up being 60. That is definitely not less than 0. So this is not true at that location. This centerpiece here, well, 0 is obviously in that center group, so let's try x equals 0. If we put 0 in for x, x squared is still 0, so that's just 2 times 0 is 0. 3 times 0 is 0. 0 minus 5 is definitely less than or equal to 0. So that is a solution. In that area, the values that are between those critical values, those boundary values, do make that inequality true. And of course, up here, let's use positive 5 and see how that works. 5 squared is 25, times 2 is 50 again. 3 times 5 is 15. Well, that adds up to 30. That is definitely not less than or equal to 0. So it is not true over here as well. So what that means is that we're true between those values, and because this is or equal to, we are true at those values. So if I were graphing this solution, I would either do a closed dot on each end to indicate that the -1 and the 2.5 were included, or I could use the square brackets on the end. If I were doing set notation, set notation would be all values of x such that -1 is less than or equal to x, which is less than or equal to 2.5. Interval notation. Well, this is inclusive, so it's a square bracket from -1 up to 2.5, or 5 halves, however you prefer to list it. So first question, does anybody have any questions on how to switch between notations from the number line to set notation to interval notation? Any questions on translating between them? We're good there? The next question is, are there any questions on how we came up with, get back here, where are you? There it is. How we came up with these boundary values, the -1 and the 5 halves. Next, are there any questions on how we determined which regions were true and which ones were false? Okay. And there are several ways you could analyze it. Here, we took a value out of that each region, we just put it back in the original inequality. We could have done like we did yesterday, where we put that value into these factors, knowing that to be less than or equal to 0, one factor had to be positive and one had to be negative. So that would have worked as well as we did this. The -5 would have made both factors here negative, so that wouldn't have worked. The 0 made one factor negative and the other factor positive, that's why it worked. And the +5 here would have made one factor positive or negative and the other one positive. Sorry, would have made both of them positive again. Anyway, let's look at another example.
So if we found the boundary though, I mean, why did we bother checking for a value outside of it? Wouldn't it have to be inside there?
Very good question. Let's take a look. If we look at this one, it's got 0 over here already, so we're good there. Let's just use the equivalent equation. It is factorable. X minus 2, x minus 3. So here we get x equals 2 and x equals 3 are the boundary values. Pretty narrow boundaries. Here, however, we want the value to be greater than 0. So let's try a value that's in between here, which would be 2.5, right? If I try that, 2.5 squared is 6.25. Negative 5 times 2.25 is negative 12.5 plus 6. That actually gives us a negative 0.25. That is not greater than 0. It's not true between those values. Hopefully that means it's true outside on both sides, but let's double check. So 0 is obviously down here. Well, 0 squared is 0, 5 times 0 is 0, 0 plus 6 is greater than 0. We're true down here. Maybe we'll try positive 5. 5 squared is 25, minus 5 times 5 is 25, so 0 plus 6 is greater than 0. So it is true up there. So what that is telling us is, in this case, we're true outside of the boundary values. And once again, this is or equal to, which means the boundary values are included. So either like that or like this is our solution. Now I'm going to give you about 30 seconds here. Give me that solution in set notation and interval notation. So, in set notation, this is all values of x such that x is less than or equal to 2, or x is greater than or equal to 3. In interval notation, this is negative infinity to 2, union with, stop making my union funny, union with 3 to positive infinity. Any questions there? Okay. I'm going to have you guys try one here. Try that one in your notes. I'll give you about a minute. So we set this as an equality, and then we factor. We would have 3x plus 4 and x plus 1. Solving each, this one is going to give us x is equal to negative 1 1/3. This will give us x is equal to negative 1. Everybody good on those boundary values? Okay. So again, we have a very narrow, an extremely narrow range here. Between negative 1 1/3 and negative 1. Between them is going to be tough to find. Negative 1.1 would be between them. So let's try that. Well, 1.1 squared, negative 1.1 squared is 1.21. Times 3 is 3.63. 7 times negative 1.1 is negative 7.7. Plus 4. Is that less than 0? Just barely. It's actually a negative 0.07. So it is less than 0. We're true between those values. Now we have to verify to make sure it's not true outside of those boundary values. We can use negative 2 out here. Negative 2 squared is 4. 3 times 4 is 12. 7 times negative 2 is negative 14. 12 plus negative 14 is negative 2, plus 4 is positive 2. That is not less than 0. We can try 0 up here. Well, 0 squared is 0, and times 3 is still 0. 7 times 0 is 0, plus 4 is 4, which is not less than 0. So our solution here is on that number line between negative 1 1/3 and negative 1. So one of those two notations, or all values of x such that negative 1 1/3 is less than x and less, oops, yes, you caught me there. I did something wrong there. What was it?
Open dot?
Open dots, yes. There we go. And it should be the round brackets on the end. And then, of course, interval notation, negative 1 1/3 to negative 1 with the round brackets. I'm not going to require you to give all three forms of the answer every time. I'm only doing it here because sometimes I'll ask for the graph, sometimes I'll ask for set notation, and sometimes interval. So we just will practice doing all three so that we're ready when we're asked. How many of you had that one right? Good. I'm going to give you an easier one. Now, of course, I say easier one, that's usually a bad omen, but give that one a shot. I'll give you another minute. We'll set it as an equality, an equation. And, of course, factoring this one is easy. It's a greatest common factor of 4x, leaving us with x minus 3. So if we solve each of those, 4x equals 0 gives us that x equals 0. X minus 3 equals 0 gives us that x equals 3 as our boundary values. So we're checking between those values. Let's start with 1 is between those values. Let's start with that. 1 squared is 1, so 4 times 1, 12 times 1 is just 12. 4 minus 12 is negative 8. That is not greater than or equal to 0, so it is not between them. So it's most likely outside. Let's double check. Let's do negative 1 to check this end. negative 1 squared is 1 times 4 is 4. Negative 12 times negative 1 is a positive 12, which adds up to 16. That is greater than or equal to 0. So the bottom end is true. Up here, let's do 5. 5 squared is 25 times 4 is 100. Minus 12 times 5 is 60. That's 40. That is definitely greater than or equal to 0. So we're true up here. So if we were graphing this, it is or equal to, so it is a solid dot going out from 0 and up from 3, or of course a square bracket down from 0, up from 3, or all values of x such that x is less than or equal to 0, or x is greater than or equal to 3, or in an interval negative infinity to 0 with a square bracket at 0, unioned with 3 with a square bracket to positive infinity. So those linear, in this case, quadratic inequalities are not horrible in one variable. At some point, we might, if we have time at the end of the semester, we might come back and do 2 variables on the xy graph, and where we shaded above or below the line before, we'd have to shade either inside the parabola or outside the parabola. That's one of those optional topics for the course. Cross your fingers, we run out of time, right? So anyway, actually they're not bad at all. We also started a little bit yesterday on rational inequalities. Rational inequalities, the word rational means fraction. So just like we were dealing with rational expressions, rational equations, these are algebraic expressions that are in fractions that are inequalities. So we might have 2x minus 8 over 3x plus 6 is greater than or equal to 0. To solve this, to be greater than or equal to 0, when it's 0 on this side, it makes it a lot simpler to work with. All we need to analyze is this result over here positive or negative? And as we mentioned yesterday, to be positive, both expressions, either both are positive or both are negative. To be negative, of course, it's just one of each. So what we're going to do in this case is we're going to solve this as 2 separate expressions. (2x minus 8), when is that greater than or equal to 0? And 3x plus 6, when is that greater than or equal to 0? So the first one will add 8. 2x is greater than or equal to 8. And we'll divide by 2 to get x is greater than or equal to 4. This one here, we subtract 6 to get 3x is greater than or equal to negative 6. And we divide by 3 to get x is greater than or equal to negative 2. So the question is, what does this tell us? Well, we're going to look at a graph again, and we have some critical values here at negative 2 and positive 4. Yesterday we talked about analyzing these separately. Let's analyze them together on the graph today. X is greater than or equal to 4. That's right here. Greater than, equal to, or greater than 4. x is greater than or equal to negative 2. Well, equal to negative 2 or greater than. These green sections on the graph represent, since I used greater than or equal to here, they represent when each piece of this is positive. Now remember up here, we said we either need both to be positive or both to be negative. So the green sections, think of this as being two separate graphs. Down here, the green section is where that first one is positive. The white section over on this other side here is where it's negative. For the top one, the green section is where this is positive. The white section over here is where it's negative. So where on this overlapping number line are both positive? Well, right up here. Both are positive here where x is greater than or equal to 4. Where are both negative? Well, down here, if x is strictly less than negative 2. Why is it strictly less than? Because if it equals negative 2, this one was true. Also, by the way, if it equals negative 2, this would be 0, and we can't divide by 0. So the solution here, this is true. Less than negative 2, greater than or equal to positive 4. Or, of course, you could have the round bracket and the square bracket if you wanted to. So our interval notation, all values of x such that x is less than negative 2 or x is greater than or equal to 4. Sorry, set notation. Interval notation would be negative infinity to negative 2 unioned with, oops, there should be a square bracket on the 4 to positive infinity. So it's just a matter of taking the numerator and the denominator, solving them separately, and seeing where the graphs overlap. Where the graphs overlap or the absence of graph overlaps. Of course, you've probably learned by now, it doesn't stay that simple. This one is not greater than 0, it's greater than 5. That complicates things a little bit. So what are we going to do? Well, first thing we have to check, impossible values. Now they kind of came out in the wash up above, but here x cannot equal 2. Why can't x equal 2? Yeah, 2 minus 2 would be 0, and we cannot have 0 in our denominator. Cannot divide by 0. Since there are no, since this is not 0 on the other side, when it was 0, if we tried to multiply by the denominator, we would lose part of the information. But since it is not 0 over here, we can multiply both sides of this by x minus 2. So we have 7 is greater than 5x minus 10. There's a big if here. Why do I say if x is greater than 2, 7 is greater than 5x minus 10? If x is greater than, oops, go ahead.
I was going to say 0 or 1 wouldn't be greater than 7. 7 wouldn't be greater than, oh yeah, it would.
If x were 0, what would this denominator equal?
-2.
So if that were negative 2, what we just multiplied by would have been negative 2, right? And when we multiply an inequality by a negative, what do we have to do? Flip the sign, exactly. So if x is greater than 2, we multiplied by a positive here, that's our result. The other side is if x is less than 2, then 7 is less than 5x minus 10. So we have to explore both possibilities. So if I solve this over here, for x, I'm going to add 10 to get 17 is greater than 5x, and I'll divide by 5. 17 divided by 5 is 17 over 5, or 3.4 is greater than x. X is less than 3.4 is what that's saying. Let's go over here and solve this one. Over here we would add 10. We would get 17 is less than 5x. Dividing by 5 gives us a horrible contradiction, doesn't it? That would give us 3.4 is, oops, sorry, I got to be careful here. When I do that, if I multiplied by a negative, that would actually be a negative 7 now. So when I add my 10, this would be 3 is less than 5x. Dividing by 5 would be 0.6 is less than x, or x is greater than 0.6. So what we have here is a few critical values on our graph. We've got the critical value of, so 0 here, 1, 2, 3, 4. We've got that critical value of x equals 2. From 2 down to 0.6, we've got to check to see what's going on there. And then we also got up to 3.4 that we have to deal with. Well, let's check. If we put in 0 here, do we get something that's true? 7 over negative 2, is that greater than 5? No, not true. If I put in 1 here, does it make it true? Well, no. 1 minus 2 is negative 1. 7 divided by negative 1 is not greater than 5. That section is not true. Let's look in this section here. Let's try 3. If I put 3 in there, 3 minus 2 is 1. 7 divided by 1 is greater than 5. It's true there. If I put in 4, Well, 4 minus 2 would be 2. 7 divided by 2 is 3.5. That's not greater than 5. So it is not true out here. So of our 3 critical values we had, it created 4 regions, and only one of those 4 regions is true. It is the region that goes from the 2 up to 3.4. Now this was strictly greater than, so that would be an open dot at 3.4. So our set notation would be all values of x such that 2 is less than x, which is less than 3.4, or 17 over 5, if you want to put it that way. Interval notation would be from 2 to 3.4. Okay. Now the next step in our evolution here of problems is to use these quadratic methods for helping us graph inequalities. Or not graphing, graphing quadratics. We already looked at some generic graphing techniques before. So if I have, instead of y, I'm going to use f of x equals x squared. We know that that is simply a parabola with its vertex at the origin. If you go over 1, 1 squared is 1. Go over negative 1 squared is 1. If you go over 2, 2 squared is 4. Go over negative 2 squared is also 4. Get that parabola that looks like that. And some of the things we did with that, we could add or subtract to the x. And remember, whatever we did to the x, the vertex actually goes the opposite direction along the x-axis. So x minus 2 means the vertex moves over to positive 2. The other thing we could do looked like this. Now technically what this was is if there was a y here, this would be y minus 3 equals x squared. We subtracted from the y. But when we do f of x notation, we have to put stuff over on the other side. So even though that's a plus 3, we're really subtracting 3 from y. And of course we do the opposite. Subtracting 3, the opposite means we go up 3. So the vertex here is at positive 3 on the y-axis. And again, we're the same width. We can combine both of those at once. We can have f of x equals x plus 1 squared minus 3. Well, the plus 1 here, remember what's happening to the x here, we do the opposite. We added 1, so on the x-axis we go to negative 1. The minus 3 here means we go down towards the y-axis, we go down to negative 3. So our vertex is right there. Remember translating these vertexes, translating the origin basically? And again, we go over 1, 1 squared is 1, over 1, 1 squared is 1, over 2, 2 squared is 4, over 2, 2 squared is 4. We get that parabola. The piece that we haven't really plugged into this yet is a slope factor type thing, where if I have f of x equals 3x squared. So what that 3 multiplying the x is kind of like a slope. Up here we were going over 1, up 1. Well, now we would go up 3 times as much as we normally would. The vertex for this one is still at the origin, at the center here. Over 1, 1 squared is 1, but we have to multiply by 3, so we go up 3. Going back 1, of course 1 squared is still 1, times 3 is 3. Over 2, 2 squared is 4, times 3 is 12. And the same on the other side. So we get a much narrower, steeper-sided parabola. We could have a negative type slope. So what does that mean? Well, first of all, we got to locate our vertex. What would be the coordinate of our vertex here? What's the x coordinate? Positive 2. What's the y coordinate? Negative 3. Very good. So we're at 2, negative 3. That's our vertex. Now from there, this is a negative 2. So if we go over one spot, 1 squared is 1. But times 2 is a negative 2. It means we go down 2. If we go over 2, 2 squared is 4. Times negative 2 would be negative 8, which means we go down 8. Which turns our parabola upside down, and again makes it slightly narrower than usual. So our big question is, how do we get our standard quadratic equation into this form? Well, it's the tools that we've been using over the last couple of days. If I have f of x equals x squared plus 6x plus 5. Remember that process we tried a couple days ago called completing the square? I am going to, first of all, use y in place of f of x just because it's just a lot quicker for our notation. I'm going to subtract 5 from both sides to make this spot 0. So I've got y minus 5 here equals x squared plus 6x, and this spot is blank. To make this side of the equation a perfect square, what number has to go there? Plus 9. So I'm going to add 9 to make that a plus 9. So over here, negative 5 plus 9 is a positive 4. This is x squared plus 6x plus 9. This is now factorable. It is x plus 3 squared. Now I need to get y by itself, so I'm going to subtract the 4. Y equals x plus 3 squared minus 4. Where's our vertex? Perfect. Vertex is at, oops, careful. Negative 3, negative 4. There we go. It gets confusing because this one's the opposite and this one's the same because we've moved it over to the other side. It can be a little uglier when I do this. because the first thing we have to do is make this coefficient a 1. So how do I make that a 1? I divide by 2. So this is y over 2 equals x squared plus 16x plus 1/2. 8x, thank you. The little hamster's watching the clock thinking I've got 6 minutes to finish this sucker up. Sorry. So we subtract the 1/2. So we've got y over 2 minus 1 over 2 equals the x squared plus 8x. Note, by the way, little side note, we could have subtracted the 1 first. Y minus 1 divided by 2 would still be y over 2 minus 1 over 2. But typically we go step by step. We divide by that coefficient of x squared first. What needs to go here? 16, so we're going to add 16. So this is y over 2 minus, plus 16 there, so plus 15.5 equals x squared plus 8x plus 16. And of course, this is x plus 4 squared. Now, I'm going to write this 15.5 as 31 over 2. The reason I'm going to do that is I'm going to write this as y plus 31 all over 2. The reason I did that, and it really wouldn't make any difference. I could have done it here as well, but I'm going to multiply by 2 to get rid of that 2. I could have done it up here. If I multiplied by 2, it would have canceled out that 2. 15.5 times 2 would still give me 31. So y plus 31 equals 2 times the x plus 4 squared. And then, of course, we have to subtract 31. So y equals 2 times x plus 4 squared minus 31. Our vertex is at what?
-4, -31.
Perfect. -4, -31. And from that vertex, because it's a 2 here, we go over 1 up 2. Over 2, 2 squared is 4, so times 2 is up 8 to get that parabola. We're running a little short on time, so rather than put in A, B, C, and all that junk, I'm just going to go ahead and give you, if we have, f of x is ax squared plus bx plus c. It simplifies to, when we do that completing the square process, similar to doing all of our to get our quadratic formula. This is going to simplify to f of x equals a times x minus b over 2a squared plus c minus b squared over 2a. We'll cover this a little bit more tomorrow. For now, homework 14B, of course, goes through the material we talked about today. We have 5 more lectures left before the final test, so make sure you are looking at that final exam study sheet. Um, 2 weeks from today is scheduled as an unscheduled day, a non-topic day. What that means is that's our day. If we're behind on anything, we'll use it to catch up. If we are caught up, I am going to use that day to answer any questions on that study sheet. So then, of course, that final Wednesday will be our exam. Because of the end of the semester looming near, I will once again offer extra credit for completing the study sheet, but that study sheet will have to be turned in by the end of the day that Wednesday, just because that'll give me time to finish up our final grades. Our final exam, I am going to give you 3 hours for the final exam. Just because there are a few cumulative questions. Instead of 30 questions, this one is going to be 40. So it's just a touch longer. So if you're going to need more time outside of class, you're welcome to either come in early or stay late. We'll discuss it more once we get closer, and I'll make sure I make arrangements at each campus for you to do that. Anybody have any questions?
Yeah, is the last test just on the stuff we've done since our test 2, or is it everything that we've done?
There's 40 questions, 30 new, 10 cumulative. The final exam, I'm trying to remember now off the syllabus. I think it was 140 points, if I remember right, instead of just 100. So, yeah, be ready for that. But everything that's fair game is on that study sheet. I realize this final exam study sheet is a monster. It was like, 16 pages or something like that. It will be plus 35 points if you do complete that and turn it in by the end of that day. But I realize it is a ton of work. So, okay, you guys have a great day. We'll see you tomorrow.